Hello, welcome back. This will be lecture 2, as you saw on the earlier slide, the idea of pointers and memory. The topic here is sort of the meat of the beginning part of C++. Firstly, because it is handled a little bit different than Java, and secondly, because of the not only is it handled differently than Java, but the fact that the pointers that we use are a little more powerful than the references in Java also opens us up to a few more errors that we might not be able to encounter in Java. The types of errors are greatly expanded, and it does require some discipline to use these ideas correctly. So we'll be discussing today the various ideas behind allocation of both local and dynamic objects, and we will also be exploring the difference between local and dynamic memory. You've probably touched on this a little bit in the previous course, but we will explore it in the context of C++. And then when that's finished, we'll talk a little bit about the deallocation issue, which doesn't come up in Java, and then we'll be done. This particular lecture is going to be longer because here locally during the class, it does cover about a lecture and a half. So this will be probably about maybe a 80-minute lecture or so, and then the lecture 3 would be trimmed accordingly to like half an hour or thereabouts. So that, just so you're warned, we're keeping it in terms of a larger topic rather than dividing it up just by the local lectures here. The notes packets on the web page are divided the same way. Lecture 2 covers everything, and it's very extensive. The third packet is relatively thin, corresponding with the relatively small lecture. Before I start, I just wanted to thank you for your patience with the class getting rolling. Things are busy here with me running about 3 different courses. And so I know the lectures we're not right like a whole bunch from out the first week like I would have wanted. I'm burning about 4 or 5 of them tonight, with and without Charles, because I'm sure he wants to go to bed at some point. So I do thank you for your patience waiting for me to get these first few lectures up on the web. And the rest of them should be well in advance of when you need them. So what we're going to be looking at today first is the issue of allocation in C++ and Java. So if you happen to come from a C background, the whole idea of objects will be new, but dynamic memory won't be, or the difference between local and dynamic memory and our ability to sort of grab large chunks of memory. It's not new in Java either, but it's handled a little bit differently in Java than in C, simply because we've got object orientation. So I'll try it again as I try to have done a little bit over the lectures I've dealt with already, to tie things back in a little bit to C for those of you who may have come from that background, because again, I'm not exactly sure what all your backgrounds might be. Though I hope you've all had object-oriented programming, you may not have. So in Java, we had 2 abilities. The first was to make local declarations of primitive types. So for example, you could say int n. Now, of course, we could do that in C as well. That's nothing new. The other thing we could do in Java was to make dynamic allocations of user-defined types. And so that idea was when we said, for example, new chord. That expression. Of course, you'd use that in some larger expression like C3 equals new chord with a semicolon, but that expression by itself was what actually allocated our memory. In C, we didn't really do too much dynamic allocation of objects because we didn't have the idea of objects defined, but you do have the idea of malloc and free, and so this is essentially the Java or C++ version of malloc and free, where you actually have a type defined, and then that type is what produces the size of the memory you're going to allocate. So if that idea is new to you, that's what's going on. This is a class is essentially, you may have gotten the hint last time if you're from a C background. A class is similar to a struct in C. It's a named collective type. And all we're doing here is we're trying to allocate enough space for that type. So this is a dynamic allocation in all 3 languages. What Java did not give us the ability to do was to have these concepts switched around. In all 3 languages, C, C++, and Java, we can have local declarations and declarations of user-defined types or library types. or in C it would be just the idea of dynamic allocation of some chunk of memory. In C++, unlike in Java, you also have the ability to do two more things other than Java allowed you here. You have the ability to say we can have local declarations, just like here, of the user-defined types. Meaning we can go ahead and say chord C1. And so in Java, that was creating a reference C1. Here, it looks exactly the same in terms of syntax, but it does something different. In C++, what we're doing here is creating an object C1. And we'll look at this in an example in a second. But what we're doing here is actually setting aside all the memory needed for a chord object. In Java, we would have had to do this, and it would be the new chord statement that would actually set aside the 4 cells needed for a chord, assuming a double takes 64 bits, and from lecture 1, our class chord needed 2 doubles. So we would assume then, for the sake of our example today, that a chord needs 128 bits. This would set aside 128 bits in dynamic memory. This expression here in C++ sets aside 128 bits in local memory. Not just space for the reference, as in Java, but space for the entire object itself. And that's a key difference that will then factor into some of the things we talk about over the next 80 minutes or so. C++ also adds the ability to do dynamic allocations of primitive types. So for example, we could say new int in C++, or we could say new int, and we can initialize it with some value. We will, in lecture 5, get into the idea of constructors in C++ and what happens when we pass in values into those parentheses. So we will go back and touch up on that if you're not familiar with constructors. But you can think of the primitive types in C++ as having their own version of constructors, which would be, I guess, initializer functions. This would be the equivalent of creating the integer and then assigning it to 5. We're just saying now here, make it 5 directly, and we could have actually done that up here. Int n, and we're assigning it to 2, though we tend not to do that, but we do have that ability as well. So the idea is that our integers sort of have these initializers if we want them, and so do floats and chars and so on. They're more useful with dynamic memory, though. So those are the 4 abilities we have for declarations in C++. In C, the things didn't really come into play here because it was either local or dynamic. With malloc, we didn't have a hugely intense idea behind the object creation. Java allowed object creation and saying new instead of malloc, but we did have then the idea of you were only able to dynamically allocate user-defined or library types. In C++, you can also make local versions that will then go out of scope just like integers would. And in C++, you can also make dynamic integers that will remain in scope just like the chords would have. And so in Java, the summary, I guess, would be in Java that local declarations are tied to primitives, dynamics are tied to user-defined types, whereas in C++, whether an object is local or dynamic, and whether it's primitive or user-defined, those are completely separate issues. And therefore, we have 4 combinations rather than 2, and therefore 4 options rather than 2. So what we are now going to do is look at an example, and this is a memory diagram we will be making use of. If you're unfamiliar with the notation I'm using here, the pointer to the packet 2, the pointers in memory packet on the web page, what this entails is what we've essentially done is started at section 3. The first 2 sections are sort of background information that we're not really going to be testing on, but they're helpful to understand certain things or to answer questions that may come up as I talk about the stuff here today. They're based on the kind of questions students have had in the past concerning a little bit of computer architecture and compilation details, questions on those topics that arose as we discuss other things. So I thought, well, it would be helpful to provide a little bit of background information so as you read those packets, which are sort of our beginning C++ textbook, those first 2 sections will be helpful as background information. But the material we're concerned with starts with section 3, and if you don't have any use for those first 2 sections, then I guess you don't have to read them, though I would certainly encourage you to do so, but don't worry about studying them intently when we have the exams because they're not really part of the course material. They're just related issues. So, but the idea here is that this is a memory diagram. I've arranged the memory as a bunch of cells, and I've given them addresses. So my standard notation for addresses is that this is at address 44, this is at address 48, this is at address 52, because these are consecutive cells in memory. And if you look over section 1 in that packet, I let you know, if you're not familiar with the idea already, that memory tends to be byte addressable, which means every group of 8 bits can have its own address. And so if we're assuming here a 32-bit machine, then we have 4 bytes per word. And that is why here we've got the addresses every 4, multiples of 4, because what we really have here is 44, 45, 46, and 47 in various 8-bit blocks. And those 4 8-bit blocks form a 32-bit word, which is our memory cell. Now, if a lot of that didn't make much sense, don't worry about it. That's more of a computer architecture issue. I'm just explaining roughly why this looks the way it does. As long as you can accept these as addresses of memory cells, that's all you really need to do. The explanations involved of why it's every 4, it's not a big issue for now. So, when we declare an integer, for example, int n, the idea here is that the compiler, when it compiles that line and has a machine line spit out, or when it starts dealing with n, the compiler is going to set up a mapping. It's going to decide that there's some memory location that n should correspond to, and whenever n occurs later in the program, that memory location will be put in n's place. When the program is compiled, there are no variable names any longer, just memory locations. So let's say the compiler happens to choose A48 for n. So this will be n. Now, I'm going to, even though the machine itself won't have variable names on the compiler level, I'm going to go ahead and draw variable names attached with dotted lines to our cells anyway, just so you're aware from the diagram what variable name goes with what cell. And now this variable, when we declare it in C++, unlike in Java, is not given any kind of a default value. The rule in C++, or one of them at any rate, tends to be no overhead. The idea being that the language doesn't force you to do anything you might choose not to do. One of those things is initialization. So as a result, whatever electrons happen to be sitting on the hardware, that's what the value is of n, and we have no idea what that is. So let's draw a question mark there, and I'll come back to that issue in a second. The idea here is that if the machine were to automatically assign n a value, such as how Java automatically gives integers the value 0, that would be an extra machine cycle that you might choose not to want in your program. If you say, listen, I know I'm going to write a value into n later on, I don't want to initialize it now, then you could make that decision, save yourself the extra machine cycle, and therefore optimize your program ever so slightly more than it would have been optimized otherwise. And C++ gives you that power in a lot of different places, the ability to make the small adjustments that can speed up your program just a little bit here and there. Java restricts you from doing those things. As a result, it's a simpler language. C++ will give you the ability to do those things. As a result, there's a lot more rules to keep in mind about behavior and such, because a standard trade-off would simply be with power comes the responsibility to use it correctly. And however true that may be in life, that's true in computer languages as well. So you have the concept here then of the variable has a name or a location, and a variable will have a value, and I should actually, it has a location, a value, and a name. Those are the three things a variable will always have. And so the idea here is that the location is where it's located in memory. Here, n is located at A48. The name we gave to this cell is n. The cell is at A48, and right now it has no value. And so we're not quite sure what it holds because it's garbage memory. The electrons form some pattern, could be 10, could be 1860, could be negative 0153986. We have no idea. It doesn't matter. We don't want to read n until we've written it. And a good compiler will probably warn you if you're doing that. But we want to make sure we don't do that. And so that value there is commonly termed garbage, because it's not really anything of relevance to us. It's just some trash that's sitting there until we overwrite it. So this is a garbage value, and that's how we would signify it. But this is the key idea, is that every variable has these three things: a location, a value, and a name. Now, as far as the value goes, and I'll write that a little larger, I'll have this in a summary sheet in a second, so I think I wrote it a little too small there. It'll show up in a minute in a larger form. As far as the value goes, right now we can think of the value as being this garbage value until we have a statement such as n equals 5, because now we're taking the value 5, writing it into n, That changes the pattern of electrons on that hardware, and now the value can be thought of as 5. And so if we were sort of to put up a summary of the status of this integer right here, we can say, well, here it is. We have the idea of a where, a location, and this would be the idea of the location here. It's at address A44. The address I'm sorry, we haven't done that yet. A44 was where I meant to put it. I'm just going to change this to A48. That's what I meant to put there. Sorry about that. So A48 is where the variable is. What the variable holds is the value 5, and how we refer to it is n. And so I've got both listings in the notes packet. I refer to it as location, value, and name, and I also refer to it as where, what, and how. So you get the idea of two different ways in which this variable has 3 key components to it. And those are going to be important to keep in mind, because when we start dealing with dynamic objects, it'll be missing one of those components. But for now, the variables we deal with will have all 3 of those components. The other thing to keep in mind here is that we're about to look at chord next. These 3 components don't change for other variables. We'll have a user-defined variable now, and the 3 components will be the same. Location, where it's located, what value it holds, and how we refer to it, what name it has. Those will be the same for our chord variable that we look at next. They will also be the same for the pointer variables we look at a little bit later in the lecture. And so as a result, the commonality I'm trying to tie in here is the idea that all variables have these same 3 ideas, these same 3 pieces of information. If you keep that foremost in your mind, it'll make pointers a lot easier, because it'll make you realize that pointers are not fundamentally really that much different than anything else. They just happen to be variables that have a few special properties. And we'll talk about that a little bit later when we actually explain what a pointer is, instead of just having me refer to the name. So, actually, let me just go ahead and keep this up. So as far as our 4th slide goes, on your, I guess, my left, your right, we can now consider the declaration chord C1. And what this is going to do is, in addition to the integer that's already there, it's going to grab memory for a coordinate. And assuming this chord object contains 2 doubles, x chord and y chord, as we looked at last time, and if each of those doubles takes 64 bits, which we'll just assume for the sake of the example, then the idea is that we will need 4 memory cells, 64 bits or 2 32-bit words for the x chord and 2 32-bit words for the y chord. So let's say our local allocation happens to grab that chunk of memory for us, and you'll notice, of course, I've left off some cells in between various sections. Those are the 4 cells we're concerned with. So the idea here then is that C1 is going to be located in these sections of memory. It will have variables or values, but those values will be garbage because we have not initialized x chord or y chord yet, and the name will be C1. Now I'm going to draw this on a different memory diagram. So we will have this idea here. And of course, we should have n there as well, the n information. So here we'll have the original question mark that we had overwritten with 5. And now we have C1 there, because we had said C chord C1. So the variable C1 here has as its location, well, we're going to come back to that, has as its value sort of a pair of garbage values, because we haven't initialized anything yet. And it has as its name, of course, C1. And again, those 3 components are what this object has. Now, in order to initialize this, we need to use a member function. Or if you're familiar with Java terminology, we need to invoke an instance method. And we looked at an instance method or a member function last time, the initialize function. And the way we run that on this object is to list the object itself, and then followed by a dot, followed by initialize. And here we'll have 3.1, 6.2, just to pass in whatever values we want there. The idea then is 3.1 is written into X chord, 6.2 is written into Y chord. So this line is how we would initialize. And if you have a Java background, that should look somewhat familiar. In object-oriented programming, or at least in C++ for the local objects, that is how we invoke member functions. We list the name of the object, or some stand-in for that, as we'll see in it shortly. And then we follow that with a dot. So we have object dot, and then the initialize function, or whatever other member function we're trying to call. And the initialize function then runs on that object, referred to by C1. And so the initialize runs on that object and initializes the X chord and Y chord of this object, as opposed to some other chord object, to 3.1 and 6.2. So now the value here, of course, is 3.1, 6.2. The location is also important. We have here 4 cells, and the question is then, what's the location? And the answer is we define an object's location by its first cell. So our location here all along has been A128. Of course, it does take up other cells as well, but everything's always going to be defined with a starting point, because when we start looking at pointers, they will be similar to Java references in the idea that the pointer or the reference stores the location of the object. And so that location, that starting location, is what we need. When you compile your code, what will have happened will be that the various fields, the various member data of this object would be defined in terms of an offset from the starting point. So you'd say here that X chord is 0 bits from the starting point, which is A128. Y chord is 64 bits from the starting point. And so starting at 128, 64 bits is 8 bytes, and you add 8 bytes to 128, and that gives you 136. That arithmetic is not something you need to worry too much about. The whole idea, though, is simply that Y chord is defined as being a certain distance from the starting point, and if you had some large object with 10 variables, they'd all be defined as some certain consistent distance from the starting point, and so that's how you're able to access individual fields in memory. When you want Y chord so that you can assign it the value 6.2, Y chord is some distance away from the starting location, which is 128. That's chord C1. You have A128 there, you have the 3.1, 6.2 is your value, and the name is C1. And there is your local object. Both the integer object and the local object are going to vanish once this function ends. Whatever the function was that these were declared in, they both have local scope. And we'll take a closer look at local scope in just a bit, but the idea will be that both the integer n and the C1 are local variables, and they only have scope existing till the end of the function. So at this point, I would generally ask for questions, but of course, there are no people here to ask questions. So if you need to think about that for a bit, go ahead and pause, and then you can start it again, and I will move on, because I'm moving on now. So what we need to explore next is the idea of pointers. We need to take the same chord memory, so I'm going to cover this up essentially with a new piece of paper. And we're going to discuss the idea behind pointers. So this, as I write these items, they should show up, or they eventually will show up in a big clump on slide 6. The idea of pointers are very much like Java references. The concept here is that we're going to be creating a variable that holds a memory address. And the way we do this in C++ is by putting an asterisk, that's an asterisk, this character, after the int. So we say here that our type is int pointer, and the variable of type int pointer that we're declaring is my pointer. And that shows up wherever it happens to show up in memory. Let's say it's down here at A268. So here we have my pointer. The idea now is that my pointer is a variable. Its location here is at A268. Right now it's got a garbage value. And its name, of course, we've already established is my pointer. Now, what my pointer holds is a memory address. So the first thing I'm going to do is write this line. and I'll say my equals A44. Now, we will not actually be hard coding addresses like this. Even if we wanted to, this is not actually the legal C++ syntax to do that. So don't ingrain that line in your memory because it's not actually legal code. I'm simply taking advantage of the address shorthand I'm trying to use. We can assign addresses into pointers, we just will tend not to. So the specific mechanics of how you would actually go about doing that are not important for this class because we won't really be doing that at all, except for the null address, which I'll talk about later. So don't worry that that's just pseudocode because the real code is never going to be used, and so you don't really care about the real code or the pseudocode. This is just a stopping point to what I plan to discuss next. But for now, we have some sort of address stored here. So we have two addresses involved in this situation. Note that the first is A268. That is where this variable is stored. A pointer variable is no different than any other variable. The integer held 5, the coordinate held some stuff, the pointer variable held some stuff. Each of these is located at some location, and each of them has a name. So again, there's this commonality across variables where each of these has a location, a value, and a name. The only difference between pointer variables and other variables is that the values that pointers hold are actually relevant to the machine. When you hold a 5 in an integer or 3.1 and 6.2 inside the chord, no one cares but you. Those data are only relevant to you. When we hold A44 down here in my pointer, that is the address of one of these memory cells. And because it's relevant to the machine, that means that the machine can make use of it if we have the operations to do so. And so we are going to be looking at two of those operations. First one will be dereferencing, and the first one will be address of, and the second one will be dereferencing. And we will look at them in a second. The essential idea, though, is that if I'm holding A44, the address A44, I will have the capacity with these operations to refer to this cell up here. And that does me no good whatsoever because I'm unable to refer to that. I'm unable to do anything with that cell. There's nothing stored there. Who cares? I could write stuff there, but it's not relevant to me right now. What seems like it might be a little more interesting, however, is to store the address A48 down here because that's the address of n. And so if we store the address A48 down here in my pointer, what we are essentially doing is using this pointer variable to store the address of some other relevant piece of memory. And so that's going to bring us to the first operation we'll look at. And now this should change to slide 7. This is the idea of the ampersand, which is the address of operator. I want to point out at this point that when we are dealing with symbols in the language, symbols have different meanings in different contexts. That should be something you're familiar with somewhat already. Certainly what we've just seen is that when we declare a pointer, you would say int asterisk and then your variable name. That asterisk, of course, has a different meaning when it's between two integers. Then it means multiplication. And likewise, the ampersand, just like the asterisk, will have different meanings in different situations. So we're going to have one meaning for it right now. When we hit lecture 4, we will see a different meaning for the ampersand that will occur, and the context will be different. Instead of having it inside the braces of a function, it'll be the top line of a function, and so then the ampersand will have a different meaning. And that's our intent there. So the address of operator is placed in front of a variable. And when this expression is evaluated, it will be evaluated to, in this case, A48. That is, this literally will give you the address of the variable that it comes in front of. So here is where we start to be able to not hard-code addresses and still use pointers, because instead of saying my pointer equals A44, I can instead say my pointer equals address of n. And that would store instead A48 inside my pointer, because A48 is the address of n. Now, this doesn't seem like it does anything really spectacular at the moment. That will not come till we look at the dereference operator on the next slide. But the thing to take note of here now is that my pointer holds the address of n. So there's now a relation between these two variables. Or more specifically, there is a relation between the variable my pointer and this cell. This cell could have been called anything, and whatever else, or we could have held A44 as we did earlier. The idea is that when my pointer holds A48, then we could just as well have said, well, if I want to use A48, I don't need to use the name of A48, which here would be N. I could use this pointer because that directs me to that cell. And that's what we will do with the dereference operator. So here's the address of, if when you look at now cell number 8, that's the dereference operator. And the idea here is that we will put the dereference operator in front of pointer variables. The address of operator could go in front of any variable. I said about 100 times already, every variable has an address. So we can put the ampersand in front of any variable we like, and that will produce its address. The dereference operator, however, will only really make sense in front of pointers because the goal here is to read the value of a pointer variable. And so if you don't store an address in your variable, if you are instead an integer variable or a float variable that does not store an address, then dereferencing it wouldn't make much sense. So what we will do here is have an asterisk in front of my pointer, and this is the equivalent, basically, of using n. So just as I could have said n equals 5, or I could have said print n, I could have just as well done the same thing with dereferenced my pointer. I'm going to explain that in a second. First, I want to point out this is not actually how we print in C++. It's pseudocode because you're going to see the printing syntax in your first section rather than in lecture. And so until you learn that printing syntax, I don't want to use it, though some of you may know it already. But for now, I'll just say print n as a pseudocode for printing until you are aware of how printing is actually done. So the idea here then is that the line n equals 5 is functionally equivalent to saying dereference my pointer equals 5, because what we've done here is we're saying we have my pointer. When we dereference my pointer, we are saying, when we say dereference, examine this pointer variable. It should hold an address, because that's what pointer variables hold. Jump to that address, and that cell is what is relevant to me. And that cell that is relevant to me is the key phrase here. When I say n equals 5, I'm basically saying, check out the cell that n names. That's the cell that's relevant to me. In both of these cases, we're attempting to write into a particular cell. And in both this case and this case down here, we are attempting to read the value of a particular cell. In both cases, that cell is A48. In these two cases, we're writing to the cell A48. In these two cases, we're reading the cell A48. And what we've got here in code are just two different ways of accessing that cell. The bottom version, which you are probably more familiar with, deals with the idea of giving the cell a name, n. And if we use n, that's understood everywhere to be a stand-in for this particular cell. On the other hand, up here, we are not using the name of the cell. We're going through the address. So by saying dereference my pointer, we're saying leap directly to A48 because A48 is held in my pointer. Read the address in my pointer, and then jump to that cell. That's what the dereference means. So we read A48 in my pointer and jump to cell A48, as opposed to check the compiler table and figure out what n maps to and jump to that cell. So it's the same basic idea of determining that we need to go to a certain address and jumping there. With variable syntax, we're simply going there because that's the cell that n maps to. Here, we explicitly have held that address, and the dereference will bring us there explicitly, given a pointer variable that holds the address. But in both cases, we are given the cell at A48 to either write to or to read. So that is the syntax involved for dereferencing. When you put the ampersand in front of any variable name, you get the address of that variable. When you put a asterisk in front of a pointer variable name, you dereference that pointer to obtain the object at the address it points to. And so here we obtain the integer at A48, and we said my pointer pointed to A48, which happened to be n. Now, inevitably, the question would arise in a lecture, the main lecture, why would you use this instead of this? And the answer is, in this case, you wouldn't. We will see situations very shortly where it's relevant to use the pointer syntax, but here this is going to be superior. They're functionally equivalent, but this will require a little bit more time because there's an extra operation to dereference your pointer. So there's no reason not to use this right here, but there will be many other relevant situations where this is helpful. So, and when I say no reason, there's always an exception, there's always a reason. I'm simply saying there's no reason we're going to concern ourselves with to use this when we could use this instead. So this would be the way to go. There's no reason not to that we're going to be concerned with, and this will take a little bit longer. Do note that you can do the exact same thing with the chord value. So let me start a new example here on the side. Same thing would apply here for user-defined types. We have chord reference C3, and that will create a pointer to chord, as you can see on cell 9, or slide 9. So we have here C3, and C3 now will be a name of this cell. The address of the cell is 272, or ACE272, and the value inside the cell right now is garbage. But I can say C3 equals the address of C1, and once I do that, then I overwrite that garbage value with A128, which is the address of C1, and now I can access the object through C3 by dereferencing it. Same way I can access C1. I'm about to ask questions. I will give you a moment to think about that. And then that's basically how pointers work for us in C++. They're very similar to Java references. They are simply variables that hold memory addresses instead of integers or floats or chars or whatever else. But because they hold memory addresses, this enables us now to use them to store the addresses of other variables or to store the addresses of objects that don't have names, as we'll see very shortly. So the point of the pointer here is, the intent of the pointer is to store an address, and then we will use that to refer to other memory cells at that address, and this is known as indirection, which turns out to be a very helpful technique in many places, both simple and complicated situations, and we will talk about that a little bit more as the lectures move on. So we're leaving these diagrams now. Our intent right now is I'm going to talk a little bit about stack memory and dynamic memory. There are consider think of two different kinds of memory in the system. Hopefully you're familiar with this already. The concept that when you declare variables locally, they leave, vanish, go out of scope at the end of whatever function you declared them in. And on the other hand, you have dynamic memory, which you allocate using malloc or new in Java, malloc in C. And in those cases, then that memory persists until you would get rid of it somehow, whether through explicit deallocation in C or by letting the system just gather it at some point in Java. So we'll talk about that dynamic memory in a second. The first thing I want to do is explore the idea of local or stack memory. So we will have here a memory diagram again. And let's say we have A12 here. We have whatever stuff we have elsewhere. A12, A16, A20, however deep this goes. Now, of course, we might have a whole region of stuff here above A12, or the number A12 may have actually been an even lower address. You have more than just the local and dynamic sections. There's also area for global and static variables as well. We're not going to get into that, but anyone who actually has some deep knowledge of computer architecture might be saying, hey, you're wrong, you've left out some details. Yes, I have. I'm trying to simplify things for the sake of everyone catching on. The areas we're concerned about are local and dynamic memory, so those are going to be the only ones I worry about in this class. So the idea here is, let me actually write A12 a little bit lower so it matches with the proper cell. The idea here is, imagine we had a function main, which in C++ returns int, even though it returns void in Java. And let's say we had two local variables, int x equals 2, and an integer pointer y. So we've declared x, and we've declared y, and we've written 2 into x, and y right now is garbage, and then there may be a bunch of other stuff as well. Then, after doing a bunch of other local declarations, we go ahead and call the function a, and we pass an x. So we're going to go ahead and call this function. What happens here is that, to simplify things a bit, we have set up a region here in memory where we have the items from main. And so this is the region of memory where we have local variables and any parameters we sent into main. This happens to be known as a stack frame, though that terminology is not something you'll need to know. You just might hear me refer to it every once in a while, but we're not going to test you on it. It's more of a CS232 topic, as is many of the mechanisms for making this work. We're simply concerned with pointing out a few key errors you want to avoid. So now when we call a, the idea here would be that there's some other function, a, here's int n, and then perhaps we declare a variable k as well. K equals 7, say. Well, we have another stack frame set up for a, which isn't given a definite end until we call some function from a. So the ideas are we have plenty of room here to grow our functions, but once, as in right here at main, we call another function, at that point, adding new variables to that function main ceases while we jump to a. And the memory immediately under main is given over to a, and so here we have, this other extends as deeply as you need. And then down here somewhere at A60, we would have here the variable n, which is given the value 2, because 2 is passing for x, so 2 is n. And then here at A64, we have the variable k, which is given the value 7, and so on. So we've got plenty of memory to build downward from in a until we call a function from a. Then a stack frame would be sealed off, and however long this was. And we would then build the new function if we called b from a. Now this would be, for the remainder portion of memory, b's stack frame until we called something else from b. And that's why scoping rules work the way they do. The concept is if we call a from main, b from a, c from b, and so on, we're basically moving into consecutive areas of memory that hold the local stuff from main, a, b, and so on, which means that when I return from whatever I called from b, and I return from b back to a, and I return from a back to main, all that's going on as we return from functions is a transfer of control. Whose stack frame controls the data? Before main calls a, main is in charge. Once main has called a, but a has not yet returned, main's variables are stored safely for when we go back to main, but it's the stuff in a that is of greatest concern to us. And when we return from a, this memory is all wiped out. I mean, certainly physically it exists still, but in terms of our program being able to use it, we consider that to be out of scope, and it's no longer usable. And this brings up a very, very big problem that you need to be very careful of not to do. Do not return addresses of local variables. So for example, if I had said y equals a of x, and my return type here was integer pointer, I may have said here as my second line, return the address of k. Instead of returning nothing, what I'm going to do here is return the address of k. And so far everything seems to be okay. Here I have an integer pointer. I'm returning an integer address, the address of k, which is an integer. Here I have a result, which is an integer pointer. I'm storing it inside y, which is an integer pointer. All the types seem to match up very nicely. However, we have a problem, which is that now that y is going to hold the address of k, that means, well, k was at A64. Y is going to be stored at A64. And as soon as we're holding the address of memory that's been wiped out, what that means is that the pointer y doesn't point to anything reasonable. It holds the address of a variable that technically no longer exists. The problem is, yes, there are electrons sitting in the machine. and they will probably continue to resemble the number 7 until you overwrite that cell with something else. So I could still, from y, I could say the dereference y and print it out, and I'll get 7. The problem is that this is very, 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 very unsafe, because as soon as you call b from main, if right here now you call b is going to take over this area of memory, write its own stuff into those cells, and suddenly your 7 is gone. 1 minute you've got it, 1 minute you don't. And that's not really a reliable way to write software, to just have variables vanish on you like that. And plus it can be very frustrating if you're lucky. And this is an interesting thing about C++ for many different types of things that deal with pointers and addresses. If you are lucky, the program will crash when you make such an error. And you might wonder, why on earth would that be lucky? And the answer is, the other situation that can happen is that the program doesn't crash, but instead continues on indefinitely with a bunch of erroneous data. And that's even worse than crashing, because what you'll find then is you'll be printing out a value and it suddenly changes. It's one moment it's 2, the next moment it's 851389352 or some long garbage value like that. And that's basically why, because you start overwriting your existing data with new ones. So a good rule of thumb is do not return the addresses of local variables. It's very, very, very bad. And this is why, because now essentially we're referring back down to here, and any manipulation we do of that 7 is going to be illegal and make no sense and be voided and give us serious trouble the minute we write things over that memory cell. Now, this wasn't a problem in Java. We never had to say, don't return the addresses of local variables in Java, because you couldn't. The only thing you could return were reference variables, and those reference variables held the addresses of dynamic objects. But in Java, you could never say int x and then store where x was located. It simply wasn't possible because addresses were not data in Java. Everything was fully abstracted away. Where in C++, we can actually read the addresses in our variables, and addresses are a very real form of data. And so as a result of that, we have the possibility here of returning the address of some local variable because we can obtain it. In Java, we couldn't obtain it, so we couldn't return it. In C++, we can obtain it using the addressive operator and the local variable name, and so we can return it. So with that power comes the responsibility not to use it, because you don't want to return addresses of local variables for the reasons we've outlined. So that's the idea of stack memory and why the scoping rules exist. They exist because when you leave a function, its stack frame is destroyed. And so it wouldn't make any sense for the scoping rules to say anything other than local variables of a function cease to exist, because quite literally they do. Now, moving on to dynamic memory, I have another small diagram here. Dynamic memory involves the use of new. And so unlike just saying chord C1 semicolon or int x semicolon, when I use the term new, and here we're dealing with dynamic memory or memory from the heap, rather than back at slide, which I believe was 10, and that in that situation, this was, let me write down here, local or stack memory. Local because it's memory that disappears when you're done with that function. Stack memory because it is building like a stack, where you have piles of functions, one on top of the other, or one below the other in this case. That is why that is given the term local or stack memory. The dynamic memory can change. 1 minute it could be in use, 1 minute it could not be. So that's sort of where the dynamic word comes in. And the idea is that this expression alone does two things, and this is especially important for you C programmers who may have not seen this yet, if there are any among you. Step one is just like in Java. You will allocate the memory you need for this object. And so we need 4 cells. Let's grab these 4 here from the heap. And as I mentioned here, it's called the heap. It's a bunch of collection of blocks that we have available to us. This is different than with stack memory, where we have an ordered arrangement where we have here main stack frame and then function A and then function B and C, and they follow each other one after the other. Dynamic memory is just, here's a bunch of memory, it's all connected in various ways. When you request a certain size block of bits from the memory management algorithm, it finds an appropriate size block and gives it to you. And that's what's going on. There's no ordered means to the idea of which blocks come next. It's just a big jumbled connected mess, and you go ahead and you pick out what you need from there, as long as it's all consecutive. So that's essentially what goes on with the heap. When I say new chord, I'm grabbing 4 cells from the heap. Then this is the second part, where I say now calling the constructor to initialize this object. We will look at that in lecture 5, and we'll see how to initialize it. For now, the constructor does nothing because we haven't written one, and so we simply do this. We have question marks in the x chord and the y chord spot. The top 2 cells, of course, being the x chord and the bottom 2 being the y chord. So that would be what happens, would be a constructor would be called that might potentially initialize those garbage cells if we in fact had written a constructor, which we have not yet. But that will be in lecture 5. What we really need here is a step 3, the same one we had in Java, where we say first create a reference, or in the case of C++, create a pointer, and I'll put that at C3 here. And then you would say C3 equals new chord, and that equals is step 3. C3 equals new chord, followed by a semicolon. We allocate the memory using new. We call the constructor to initialize it, and here the constructor did nothing, so there's nothing to do. Then these 2 steps together will return the address. The operator new sends back the address of the block it's just created. So these 2 together will return A10468, and that is then stored inside C3. That is how that C3 equals new chord line works. First, new chord allocates the memory, and it knows what appropriate size is involved because the compiler will keep track of how large a chord is, how large something else is. So here we're saying, well, we know how large a chord is. It's 4 cells. Give me that block. Step 2, call the constructor to initialize that block. Step 3, take the address and return it somewhere else, so that we have this picture. C3, and then that would be pointing to that block. So that is the idea behind dynamic allocation. Now we have ways of using this memory as well. We could use the standard idea of saying, well, first dereference C3. If you dereference C3, you're saying, give me the object that is at the address stored in C3. So if you give me the object stored at that address, because that's what's stored in C3, that jumps you down here, and lo and behold, there's the object you're looking for. So you can say dereference C3 first, and then call the initialize function, 2.1, 3.7. Or we have an alternative available to us as well. When you are using just objects, local variables, I can say object.initialize. What I've done here by dereferencing C3 is given me the entire object. C3 stored an address. When I dereference C3, I get the object, the memory allocated memory block stored at that address. And so that's why I would dereference C3 to get the object. And then here, once again, we have the syntax of object.member function, which is what we want. However, this deallocation and then member access with parentheses and such, that's kind of a pain in terms of syntax. So we have an alternate way to code this up, and that's through the arrow operator. It's, again, a member access operator like the dot, except this one works on pointers. Here, just as we said C1.initialize, or the effective object.initialize, when we're going straight from a pointer to the object it points to, we say C3 arrow initialize. The arrow is made up of a dash and a greater than symbol, and that would be how you type it. So we do have the ability to access from pointers to an object as well as from the object itself. The difference is, of course, the object itself would have the name, so we'd say name.initialize, or you could effectively obtain the object. If you want to stay with the pointer, then you use the arrow syntax. And we will see both many, many times over the course of the semester. Of course, once you run initialize, then you have here 2.1 and 3.7. Now the problem here is that we may run into interesting other code as well. And so effectively what we have here, and you can see this on slide 12 as well, to your right, is the concept here of, well, first we did this, chord pointer C3, then C3 equals new chord. So far, so good, right? Problem happens when, whoops, C3. And the problem happens down here when we say C3 equals new chord again. Getting for the minute that there's a big space there where I'm going to write something later on. The idea here is that this line will grab us a new chord somewhere. Remember, step 1 is a new chord. So we grab 4 memory cells. Step 2 is to initialize it to whatever is appropriate, which is here nothing. Step 3 is to write the address back into C3, which will overwrite A10468 with A10488, which is the address of first address of this cell here. Remember, blocks are always referred to by their first address. So the problem is not only that we've lost this information for the moment, but we've lost it permanently. The reason being we never had any idea where that address was. It was always stored in the pointer C3. There's no way we ever knew about it, so we can't reclaim this block. It's floating off in memory somewhere, and we're simply just stuck. And that is the problem. That is known as a memory leak. The idea of a memory leak is the concept of allocating memory and then leaving it to just float off in space. And as soon as we lose the address A0468, we can no longer get to this memory. It's effectively gone, floating in space. That means we've leaked memory. What we want to do is always put memory back when we're done with it. And for that, we use the delete operator. Form here is delete pointer. This should be an L. Don't read that literally. I'll repeat, do not read that literally. We're not deleting the pointer. We're not eliminating the pointer. What this is saying, run the delete algorithm on the address stored inside this pointer. The pointer is there just to store the address and pass it along to delete. Delete decides what to do with it. But the idea here is before you make this second allocation, you call delete on C3. That was back when 10468 was still stored in this pointer. By calling delete on that pointer, we're saying get rid of the dynamically allocated memory at this address. And so that'll wipe out that object. And the way memory management algorithms tend to store these is there's just some bit that indicates, yes, this block is being used by the program, or no, it's not. And so it's important for you to explicitly deallocate this. In Java, in the virtual machine, there was a process running around in the background, and that process was called a garbage collector. Because it collected these little bits of garbage memory. And garbage collectors were traditionally slower than dealing with explicit deallocation or deallocating memory yourself. The reason being that at this point, I know I want to get rid of C3. We don't have to just let it float off into space and try and have the compiler find it later on. When we're done with C3, we presumably know it as the programmer, even if it's not something you could deduce from the existing code. And so it's acceptable then to go ahead and delete C3, call delete on C3. That will go read the address of C3, jump to that address, and get rid of that block. And the issue then, of course, is the garbage collection tended to be slower simply because the machine had to figure out what was in use and what was not. You, the programmer, don't need to do that, so you could presumably do things faster. Now, garbage collection research has made a lot of headway in the last number of years, 35, 30 years, whatever it's been since people came up with the idea. And so, I think it's probably well before that, actually. But anyway, as a result, some garbage collection algorithms now are very nice these days. Sustrup mentions in the C++ 3rd edition that you can put garbage collection into C++. You can integrate the two together, mainly by including an existing library that overloads the meanings of new and delete. We'll talk about overloading later on. But the idea would be you can integrate a garbage collector with C. You don't have to, but you can, like so much else in C++. But Sustrup makes a point of mentioning that you can indeed integrate a garbage collection algorithm with C++. He mentions that specifically because a lot of people think there's no place for garbage collection in C++. Under the right circumstances in the right libraries, there is. And so that you may well see that showing up more and more applications as people start trying to use better garbage collection algorithms. We'll see in the future. But anyway, that's the idea here of this delete is you know at this point you can get rid of this memory. You're explicitly getting rid of it so that when you reassign C3 in a second, you haven't lost this memory. It's already been given back to the free list by indicating that it's no longer in use. And that is then a quick overview of garbage collection. The last thing we have to talk about pertains to this similar code as well, and that is the idea of null. So to introduce that, I want to mention here that reading this code would be bad. Or reading these memory cells would be bad. It's been deallocated. So if we have here chord pointer C3, C3 equals new chord, and then delete C3, the absolute worst mistake you can make is to look at that and say, well, the electrons are still in memory. I could still call a function and then go ahead and call C1 arrow initialize. Whenever you start trying to use memory that's been given back, it's just like the local variable situation. You don't return local variables to the calling function because their existence is completely dependent on not calling a new function. Likewise, the existence of this dynamic memory is dependent upon the fact that you don't create any more. So you do not want to store and make use of memory and read memory after it's been deallocated. What you want to do instead is make sure that C3 does not hold any illegitimate data. And in Java, it wasn't really possible. You either held null or you held a legitimate object location. In C++, because, for example, you're deallocating this memory and therefore C3 now, this was back when it still held 10468. When you do that, C3 would now be holding a worthless 10468. It's holding a garbage address. That was not possible in Java for references to hold garbage addresses, but it's possible here. And so as a result, we want to ensure that we don't have that cause any problems. You want to reassign it as quickly as possible. If the function ends right here with the closed brace, you're fine. If you're doing something like on the last side and immediately assigning C3 to something else, you're fine. But if you're going to have any significant amount of code after C3, chances are someone's going to be editing your code at some point, will forget that C3 was deleted and needed to be reset somehow, and will try to access the memory of C3. And now you've got a similar situation where you're reading that object even though it could be reclaimed for use elsewhere at any time. So what you want to do instead is say C3 equals to null, is equal to null, or has null written in it. Once that's done, now C3 we would often draw it as a slash through the box, and that would enable us then to test against a condition when we want to use C3. We could say here, if C3 is equal to null, then you do some stuff. Otherwise, C3, and then C3 does some more stuff based off a pointer. But the idea here would be that we can compare just as in Java, and we want to be able to make the assumption that if the pointer does not hold null, then it holds some legitimate value of a legitimate object, and we can call the arrow operator off of C3. And that's the issue at stake here. If we have a third possibility, if we are allowed to say that C3 can hold some garbage value, then it won't hold null, but this will also not be acceptable because this is only acceptable for existing objects. And if this object, we have not deleted it correctly, or if we've deleted it correctly but C3 holds its address still, then now we're going to be going to that address with the dereference and access and reading that block again, and we don't want to do that. So a good rule of thumb is as soon as you change your pointer variable to a meaningless address, assign the pointer to null right off the bat. That'll save you a whole lot of trouble reading into areas of memory you shouldn't. And with that said, that's basically all there is to say about the pointer and memory lecture. So we've looked at now 4 different ways of allocating. We can do local allocations of primitive and user-defined types. We also have the ability to make dynamic user-defined and local types. We looked at pointers, the address of and dereference operator, and how they add a little bit of functionality to what is at heart a regular variable that just happens to store addresses rather than integers. But it's a little different because it has the added functionality of address of and dereference. And then we looked at the difference between stack or local and dynamic memory and the allocations in each one. And finally, we looked at delete and the issue of garbage collection and the idea of null. And those are the things you should get out of this lecture. You will certainly have lots of experience with these topics. That'll be a major topic of the first few sections that Adam Loud will be recording for you. It will be these memory issues will be issues in your first couple of MPs. And so you will definitely get plenty of chance to practice the easy and advanced parts of what we've discussed here today. So for now, that's it. And next time, we'll talk a little bit about arrays and how they are tied into pointers in C++. See you then.